watching these lectures on iTunes these days on their iPod. So it's just it's a big responsibility for me to be to try to get that right now. I don't know if people are going to be downloading it. Hey, okay, hello everyone. Welcome. This is the 13th time I've done this in December, giving a talk about what I thought was the coolest thing I learned about trees during the year, the annual Christmas tree lecture. Well, it's usually not always the thing I learned in that year because there's so many interesting things you have to carry something over from last year. So what I'm talking about today is actually a follow-up on one of the questions that somebody asked. I think it was Lyle Ramshaw, the lecture I gave a little more than a year ago at Halloween time, when I was talking about something we called Plato-logic computing. Since then, we've changed the people in Greece didn't like the name Plato-logic, and we tossed around a bunch of Greek terms and found out that actually an English term would be better. So I'm calling that whole topic broad word computing now instead of Plato-logic computing. But anyway, I mentioned in response to one of the questions at the end of that lecture, I just made a brief reference to sideways heaps. And that's the topic of today's lecture, sideways heaps, which I think is really something that deserves to be really well known. But I don't think there's any textbooks mentioning it at the moment. And so it can be a nice part of every programmer's toolkit. So before I tell you a sideways heap, let me remind you what a heap is. In fact, it's kind of embarrassing because there are many different definitions of heaps in computer science and in mathematics with different meanings. But the kind that I'm talking about heap tonight, I'm talking about a data structure that's an infinite binary tree or a finite part of the infinite binary tree, and it looks like this. We've got nodes numbered 1, 2, 3, 4, 5, and so on as far as you want to go. And it's a binary tree, meaning that every node has, except the root, has two children. So they go like this. And just the easiest thing in the world to imagine an infinite tree that goes on and on, where we just write the numbers, as long as we can, of course, we run out of paper pretty soon, and it's pretty crowded. But it goes on and on forever. So this is an infinite binary tree that has no leaves because it never ends. It's wonderful to use this in lots of algorithms because it's what we call an implicit data structure, where we have the structure of a tree without actually storing any explicit links anywhere. We don't have to ever say in any of the nodes of the tree, this is the way to get to your left child, and this is the way to get to your right child, or this is the way to get to your parent, or to your sibling. Because it's obvious just from the address of the node itself what it is. So if you're at node K, your left child is what? 2K, and your right child is 2K plus 1. And your parent, it might come this way or it might come this way, but your parent up there is, well, what do you say? K over 2 rounded to an integer. It's a floor of K over 2. I'm going to write it in the C language notation way, K right shift 1, because we're going to be talking about sideways heaps. We're going to do more complicated shifting later, and so instead of writing, it's also I could have said K over 2, but this is going to be better for our purpose. And what about your brother? your or sister. I mean, I don't want to be sexist here. What is that? K XOR with 1, and the C notation for that is K XOR 1, but I'm not going to use C notation for that guy. I'm going to use circle plus because I like that better. This other one gets too confusing with exponents. So it's easy then to move around in this implicit data structure, saving you memory, and also if we happen to have a heap of size 10, then we would just take these nodes, and we have to make little tests at the end to see that we're not running off the end. We can increase n by 1, decrease n by 1 if we want to, but everything is compactly stored, so it's also very good from the standpoint of cached memory and other things that make computers run faster. Okay, so that's a heap. And what's a sideways heap? Okay, so sideways heap is something else that really is so simple. It's amazing that it doesn't seem to have caught on to have another name. So I made up this name, sideways heap, last year, and I don't know if it's going to. Somebody might find a better name for it, but it's again an infinite tree, which makes it a really nice implicit data structure, but it's quite different from the ordinary heap because as this name might imply, we're going to go at it sideways. So we start out with 1, and then here's 2 up here, and then 3, and then here's 4, and here's 5 down here, and the parent of 5 is 6, and then 7 and 8. Tell me when you get the idea. There's going to. Can anybody guess what this node is going to be over here? 12. Good. And this guy is going to be 10. Here's going to be 9, 11, 14, 13, 15, and up here 16. Okay. Now, I'm trying to draw this a little bit carefully so that if you project the numbers down, it's going to be in increasing order: 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 15. Because you see the so-called symmetric order of the nodes in this tree from left to right is the natural order of the integer. Okay, well now this tree, so 17 is going to be here, and it's going to go up to 18 and 19, and then 20 is going to be up here. So now, this is the sideways heap, and you notice that it has plenty of leaves. It's got infinitely many leaves, right? All the odd numbers are the leaves. And then what are the numbers that are at the next level, right above the leaves? I mean, this is something that goes way back, and number theorists have been talking about these things since the medieval times. But I mean, there's Latin terms for these for these oddly even numbers, right? So these are the odd multiples of 2. And at the next level, we've got the odd multiples of 4, and the next level are the things that are divisible by 8 but not by 16, and so on. Okay, but the thing is about this is a tree, a binary tree, but it doesn't have a root. Everybody has a parent. Nobody, it's not. So this has a root and no leaves. This has leaves and no root. Infinitely many leaves and no root. Now, guys who just came in, there's some great seats up in the front row here, and I can't lecture if anybody's standing. And in fact, my lecture improves exponentially with the number of people sitting in the front row. Yeah, very good. So now let's let's take a look at the sideways heap here. We're getting better and better and better. How do we navigate? How do we move around in this thing? Let's try to figure out a rule that. Did I lose my? Okay, repair. See, where did you lose me? A sideways heap. I see. All right, so we want to figure out how to move around in this data structure. So we want to know how to find the parent, the left child, the right child, and so on. Now, can somebody? Let's see if we can think of a formula that would take us to the parent, for example. Just consider the parent of a leaf at the beginning. So the parent of a leaf has to be some odd multiple of 2. So let's take 2007. That's a leaf. So put 2007 in binary. 1111010111, right? I don't know. I mean, I just happen to know that one. Okay. Now, what's the parent of this guy? It's going to have to be something that ends with a 0 and a 1 here. Okay. It's got to be an odd multiple of 2 because all the parents of leaves are odd multiples of 2. But which odd multiple? What are the other bits of this thing? You're going to copy them all the same here. So this is actually, the parent is 2006 of this year. Well, I guess everybody knew that. But what's the? This is the the largest. What do we call these? Oddly even number. What are the oddly even number? This is the largest oddly even number less than 2007. What's the smallest oddly even number bigger than 2007? Well, that would you have to add 1 to this thing here. To these bits all the way to the left. So that would end with a 1010. So that would be up there at 2010. So 2010, what? What's the problem?
I think you need another one.
Make you happy? Okay. I did that on purpose just to see if anybody would. But 2010, he's sitting there with his little iPhone or something. Okay, so what we're doing is actually we're rounding to the nearest odd multiple of 2. 2006, 2010, 2006 is closer. If I had been at 2005, I'd have my choice of 2006, 2002. The closer one would be 2006. So you round to the nearest odd multiple of the next guy. Well, what's the parent of 2006 then? Well, it's going to end like this, and the nearest is going to actually be copying again. So you think, oh, this is just going to be too trivial. That's 2004. So what's the parent of 2004? It's going to have to go like this. Now what do I do?
I set the bottom 2 bits to 1 0.
That seems to be right. I just set the bottom 2 bits to 1 0, and I'm in business. So that's the year 2000, turn of the century, and then the next one is going to be what? This is 2008. Yeah, that's right. We went up. 2008. Yep. I'm anticipating here. What's it going to be at this point? it has to end with 5 zeros and a 1. But now I don't want to go up any higher, so it's going to be there. So actually 2000 is the next ancestor. And now we're going to start speeding up here. This guy is 2016. Hope to live that long. What next? Oh. Well, this one is George Orwell's favorite year, 1984. And then we go, and so on. We're going to start creeping into these ones here. We're going to get 1920, and then we're going to get 1792, the French Revolution, and then 1536 and 10,024, and then we're going to zoom up 2004. We're going to go up by powers of 2 afterwards. So we've moved up there, up in the tree, and now what we want is a formula that will take us from K to the parent of K. All right. Now, here's where I might want to take a simpler thing first. I'm going to take a simpler thing first. Let's try to figure out the sibling of a node. Now, remember our node for our rule for finding the brother or sister in the heap was to do an exclusive OR of 1. Now, what's the rule here? If we're a leaf, we're going to change 9 to 11, 7 to 5, 1 to 3. What is that? That's an exclusive OR of 2 on the next to last bit. If it's up here, we're doing an exclusive OR of 4, and here an exclusive OR of 8, and so on. That complement the next to the last bit, exactly. That preserves everything. And so what's the last bit of the number K? And here we have something that I talked about when I talked about broad word computing. That's K and minus K. If you compute K and a logical AND with minus K, you get the lowest bit. And so if I now shift that left 1, it's one bit to the left of the lowest bit, and so I take K exclusive OR with this guy, and this is equal to the sibling of K. Now we can do a similar thing to get the parent of K. So I'm going to first I'm going to calculate J, forget it. J is K and minus K. This is the least bit of K. K is a positive integer, so it's always got a least bit. So this is going to be a 1 followed by as many zeros as the level we are in the sideways heap. Now I want to go to the parent. I want to round that up. And so the rule is, well, I'll write it down, and then you can see. The point is not that you can discover the rule, but that it's a simple rule. K minus J, or with K left shift 1. In the simple case that J was equal to 1. Now, if you have a leaf, an odd number the idea of an odd number is when K and minus K is 1. And in that case, what we're doing is we subtract 1 and then OR in 1 to the left. That's another way of saying this operation that I just did on 2007. What?
J shifted 1 perhaps instead of K.
I could have shifted J. No, it's not ORing it in because I have to zero it out too. I mean, let's try that. It's a good suggestion, but let's try it. If I have like 5, or let's say 6, okay. So then this is K, and then J is this. Minus K, to get minus K, you complement everything to the left of the that's minus k right there. So I ended with minus k, and everything zeroes out except for the rightmost two bits. But now if I shifted j left 1, here you mean this guy? Yeah, that's right. I thought you meant I should shift j1 before I do it here. But you're right. Yeah, I have to shift in this number, which would be 2 if j is 1, or 4 if j is 2, or whatever. Okay, so that's right. I have to OR that in, but I subtract. I first subtract, and then I OR, and that gets to the parent. So this is parent of k, and the sibling of k we got. Now the children can also be found easily, but let's go on and I guess what it is I might as well say the children of k. Just to prove that it's nice. It's k minus j right shift 1, and k plus j right shift 1. And of course, when j is 1, you don't have any children, so this formula gives you k back again. The leaves don't have any children, so this is if k not odd. So we can navigate then in a sideways heap and get around, and we have the other advantages that it accommodates. If we want to look at just a small finite segment of this, we could get a sideways heap of 10 elements, and it's almost as good as taking a heap of 10 elements, but not quite. If I look at the first 10 elements of this thing, I really sort of want to include number 12 in here too, in order to have a tree structure, because sometimes the parent will take you out of the first n, of the first n elements, but it'll never take you past 2n. It'll always be less than 2n, in fact. So it's still compact. If you have a sideways heap with with 1,000 elements, you're never going to need anything 2,000 or more. Any addresses 2,000 or more showing up in this thing, but there is this little glitch here. Now these properties with respect to data structures were, I believe, first noticed by a man named Dov Harel in his PhD thesis, 1980. And when you see a reference to a paper by D. Harel, chances are the paper is by David Harel, because he wrote more papers, whose thesis was 1978 and had nothing to do with sideways heaps whatsoever. So D. Harel, there's two D. Harels that have been doing great computer science, at least, and David Harel is my grand thesis student. He's a student of my student Von Pratt, and Dov Harel is a grand student of Jeff Ullman. So anyway, there's all Stanford connections here. You have to see somehow, but I don't think either Jeff or I realized that sideways heap was going to be a really nice implicit data structure. But if Jeff is here, he can tell me the opposite. Okay, now let's see. The people who are standing in the back, I mentioned before that the lecture gets exponentially better the more people are sitting down, and the closer to the front you sit, the better. So please come up here and sit. Now, one of the, but you say, well, okay, so it's cute, but what good is it? And one of the nice One of the nice applications is actually even more recent to some people in Finland, Katajainen, described a data structure that they found was very nice and compact. They called it a navigation pile. You see that? Yeah. So what we're doing here is I'm showing you an example of a navigation pile with 10 leaves. And in this case, it's different from 10 nodes because, but it's sort of similar. It's as if I had 20 nodes instead of if I have n leaves and 2 n nodes. But what they're doing is they're representing a priority queue with a sideways heap. The priority queue is a data structure that's good at finding the, let's say, finding the largest element. And then you can delete the largest, insert a new element, and update your data structure, and always be able to quickly zoom in, find the largest guy. And in fact, heap, that was the first application of heaps, was to use them as a priority queue and to move things around so that the largest guy was in the root. And that you put numbers in, you put data in the cells, and then you play a tournament, and the winner of a tournament bumps out moves up, and the guy up there moves down. Anyway, you get to a heap condition. Navigation pile is a different idea. You put the data all in the leaves. But then up here, you have a pointer to the largest people in your largest guy in your subtree. So under node 2, he would point to node 1 because the largest leaf in his subtree is 503, being bigger than 087. 6 similarly points to 512 here. 4 points to 512 also because the largest of the 4 leaves underneath node 4 is 512. The largest of the 8 leaves underneath node 8 is 908, so 8 points down here. 12 has 4 guys under it, 908, 170, 275, 897, 12 points to the biggest of these. So this is the idea of a navigation pile, but it's very similar to what we've been doing for years and years when we're doing something called replacement selection sort, the various things. But the new idea that made this work especially well is that they realized that these pointers you only need a 1-bit pointer for the guys at this level. It's either a pointer to the left or to the right. You only need a 2-bit pointer for the guys at the next level up, because the 4 can point to only 4 places. So you can encode that at 2 bits, 0001, 1011. And similarly, at the next level, 3 bits is all you need for the pointer. So you can pack this navigation pile very tightly into memory. The leaves are sitting here, and that's your data. It might be a whole word of data, but you can keep all of the pointers for n words of data. You only need 2 n bits to store all the pointers in the navigation pile, and instead of 2 n words. So this is a factor of 64. You're saving a lot of memory and a lot of space in cache. Now, in order to extract these pointers, you have to do shifting around and masking in the register. You have to do a little calculation, given that you want to know the pointer from node 16, for example. You have to say, well, it has 4 bits, and those 4 bits are packed somewhere. Where are they? And then you have to do a dozen or so computer operations to unpack these. But the way computers work now, that's things a computer does fast. A computer can go through a dozen instructions, zip. But as soon as it tries to access memory, it slows down because memory speeds have not followed Moore's law the way register speeds have. And so so you're often taking orders of magnitude longer when you reference memory, but just taking packed arrays of bits and shifting them around and extracting out the pointers goes fast now. So that's the idea of the navigation pile. And if you want to know where, so let's imagine that I actually was storing this in memory and packing it together. Well, I can show you here. Just as let's see, can we? Here's an exercise coming up. What I'm showing you here is a draft of section 713 of Art of Computer Programming. It's going to be published next spring. So here's the navigation pile illustration in the text, and then at the end of that section, there's an exercise 153, which says we could pack the pointers in a binary string. So the first pointer from 2 is a 0, from 6 is a 0, from 10 is 0, 14 is a 1, and the pointer from 4 is a 2-bit number. Pointer from 8 is a 3-bit number. Pointer from 16 is a 4-bit number. And the question is, what bit position from the left is for the pointer from node J? And the answer is that the number of pointers the number of bits in a pointer in J is what we call row J. This is the ruler function of J. And I talked about it in my other lecture, but this is the number of zeros, the number of zeros after the rightmost one. So an odd number row of J is 0, and an oddly even number row of J is 1, and so on. So this is the number of bits in pointer from node J in a sideways heap. And in a navigation pile, it's the number of bits in the pointer, the number of zeros. And then there's a nice identity. In order to get up to that, up to J, we calculate row 1 plus row 2 plus, and so on, up to row J. And it turns out that there's a very simple formula for this. This just happens to be J minus nu of J, where nu of J is the number of 1 bits in J. For example, row of 1 is 0, row of 2 is 1, row of 3 is 0, row of 4 is 2. Let's take J equal 4. 4 minus 1 is, J equals 4. If J equals 5, it has 2. It would be 5 minus 2 would be 1. This plus 2 plus 0, and J equals 6 would be the next case 0, 1, 0, 2, 0, 1, which would be 6 minus 2. The sum of this is 4. Right. So this is a nice identity that tells you as long as you can easily calculate the number of 1 bits in an integer, you can easily calculate where you've stored the pointers for navigation pile. Questions on this? So this is function nu j. Actually, for 50 years. People have called it the sideways addition of an integer. You sort of you take a binary number and add sideways and add all the ones in. But more recently, people are calling it the population count function, and there are other names. But a lot of computers have this built in now, so it can be done easily. Okay, now. While I'm mentioning the row function, let me mention another the dual function, which is the lambda function, which is the number of zeros. Sorry, I can't write anymore. Getting very old. After the leftmost one. So this is also equal to the floor of the log base 2 of j. But so if I have so I have a number 2007, and remember what that was. So how are we doing here? 0111. So then rho is 0, and lambda is 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. The number of digits, let's call it, of bits after the leftmost one. It's not the number of zeros, I'm sorry. It's the number of bits after the leftmost one. So it's an amazing thing that there's an identity that connects the rho and the lambda functions, and this is something that really surprised me when I discovered when I ran across it. I think it was a year ago, and that is this: that if we take the maximum of rho of I plus 1 through rho of j equals lambda of j and minus I. Don't ask me why such a formula should exist, but it happens to, it just happens that it works out, and so somebody give me an I and let's try an I and j and try to understand why this is true. So I don't know, take I equals 5 and j equals 9, let's say, okay? So rho of I, so rho of 5 is 0. So let me write it down. Rho of 5, rho of 6, rho of 7, rho of 8, rho of 9. So I want the max of this. So that's the max of 0, 1, 0, 3, 0. Okay. Now, what is 9 and minus I? So 9, this is j, is 9, that's 1001. Minus 5 is minus 5, that's, I complement everything. This is 1, 0, a whole bunch of ones here. So I add these together, and I get 1, 0, 0, 1. No, yeah, 1, 0, 0, 1, and then zeros afterwards. So I take lambda of this, and lambda of this is 3. Okay, so it just works. I mean, or at least you can pretty, you look at the sideways heap and you see why it works. So we'll look at the sideways heap, and so what we're doing is, suppose we take an interval in the sideways heap. That means you take consecutive nodes from I to j, and then so I might start at 6 or something, but then it's going to go down and go, it's going to go for a while. So what's the highest it gets? What's the highest it gets between I and j? And well, the thing is, you can compute it by this binary thing. You take j and you take minus I, logical AND of those two numbers, and then you look at the lambda function, the logarithm base 2, and that's how high it can get. And you can prove it by induction, but I don't know how to prove it by intuition. It just seems that I started writing down cases and kept simplifying until finally there it was in this calculation. So it's just a very simple thing. All right, now what I want to do in the rest of this talk is describe to you a beautiful algorithm by Baruch Sheber and Sheber and Vishkin. And this algorithm they published in 1988, and boy, it took me 2 days to doing nothing else to understand it, but it's beautiful, it's gorgeous algorithm. I'm just, at that moment I wrote down to say someday I wanted to give a computer musing on a Christmas tree lecture explaining this algorithm. It's just a fantastic, fantastically nice method for solving the problem of least common ancestor in a forest. So now, so I've got to define what that problem is, first of all, let's suppose we just have nodes in the sideways heap. Dov Harel noticed in his thesis that if you happen to have any nodes in the sideways heap, it's very easy to calculate their least common ancestor, the nearest common ancestor. I gotta say it right. Nearest common ancestor. Actually, Bob Tarjan. We got to follow his advice. He wants to call this the nearest common ancestor, and he's right. It's in a better term than least common ancestor, although it's somehow natural. But if you take any family tree, and you meet some relative at Christmas vacation, and you try to figure out in what way are you cousins. So you go back to your nearest common ancestor, and then depending on how far away that person is, that tells you how many. What kind of a cousin you are and how far removed you are. So you take any two nodes in the sideways heap, and it's not that hard to figure out their nearest common ancestors by doing this magic of anding and shifting and masking and things like that to go. Now, in general, we don't have a perfect binary structure like this. Somebody just gives us an arbitrary oriented forest, and an oriented forest is a situation where you have it's something like this. I will draw you a typical oriented forest here. B, C, let's put D here underneath A. Everybody has at most one root arc coming out of it. Every node has a pointer to a parent, except the root nodes. And we actually imagine that the root nodes have a pointer to a null parent. So there's this special magical divinity that is the parent of all the roots, but all of the mortal nodes have at most one parent, and the roots have the immortal parent. Okay, so this is an example of a forest, oriented forest. So in this case, everybody has a parent except the roots. There's no loops in the diagram, and that's the idea. So now in this particular example, there's no family that has three children in it. But the Sheber-Vishkin algorithm works in general. No matter how you can have families that are arbitrarily large. This particular example. Doesn't make use of that. But this problem of finding the nearest common ancestor of two nodes in the structure occurs fairly often in practice, where we have data that's represented with a acyclic structure like this. And we like to find the closest common way that they point to. Every two nodes have a nearest common ancestor, because if they're in different trees, it's this special node way at the top is their nearest common ancestor. So the idea is this. if U goes to V, then V is parent of U. If U goes in 0 or more steps to V, this is V is an ancestor of U. Okay. So the ancestors of what are the ancestors of G in this diagram? D, A, and G. G itself. Everybody is considered an ancestor of their self because this star notation means 0 or more times. So it turns out that it's better to have this definition where somebody is its own ancestor, because otherwise, what would be the nearest common ancestor of D and H? You know, it has to be an ancestor of both D and H, and so it has to be D would have to be the nearest common ancestor of D and H. And so, okay, so the idea is the nearest common ancestor. Let's just say the NCA of U and V equals W, which means that W is an ancestor. Okay, W is an ancestor, and every other common so W is a common ancestor, both of them, and every other common ancestor is also an ancestor of W. So I mean, formally, it says that if Z is an ancestor of U and Z is an ancestor of V, then W, or if and only if Z is an ancestor of W. This is the definition of a nearest common ancestor in logic, but the intuition is clear. Now, I want to describe to you the algorithm of Sheber and Vishkin to find the nearest common ancestor in such a data structure. And you might say, well, why am I so fascinated by this algorithm? And the reason is that it gives you the answer in the constant number of steps. No matter how big your data structure is, it just does a few calculations, zip, 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 and it says here was your nearest common ancestor. And it does this by looking at the integers that are representing U and V, and some pre-processing has gone on. So Sheber-Vishkin algorithm is not an algorithm for the dynamic nearest ancestor problem. It says you've got a fixed database, and you're going to be answering a lot of questions about common ancestors in this database. But when you have a setup like that, and so you know that a lot of people are going to be asking questions about the same structure, then you can make up a couple of magic tables, and the Sheber-Vishkin algorithm tells you how to calculate the nearest common ancestor just by a small number of computer instructions. Now, and I think it's quite beautiful, but amazingly, it's gotten bad press in the literature. As I said, it came out in 1988, and I thought that as I would keep on reading, I would find people saying, "Oh yeah, and this is this is a great thing." But instead, I find people recommending other algorithms that and saying, here's my improvement on the Sheber-Vishkin algorithm. And when I look at these improvements, I fail to see why they're an improvement, because it runs slower on the computer, and it takes me a lot longer to write the program. The only reason these other improvements are improvements, as far as I can see, is that the proof is simpler. Now, sure, it's easier to prove that some algorithms are correct, but the computer doesn't slow down when it gets to some instructions it doesn't understand. This is so I don't like this philosophy that some people seem to have, that nobody's ever allowed to write a subtle computer program. If a freshman can't understand the program, we have to throw it out because we won't be able to maintain it. This will lock computer science back at a certain level that'll never be able to advance between. So when somebody discovers a brilliant new algorithm that runs fast, so what if it takes a few pages to prove that it's correct? The computer is still going to go zip, 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 and much faster, and the code is shorter and nicer. So I think Sheber-Vishkin deserve to have their algorithm better known. I have to admit, though, that it took me 2 days to understand their paper, and it might take you 3 days to understand my write-up of their method. But it is correct, and I'll just be able to give you the basic ideas of it, and then you can look at the text when later on to see. I learned long ago it's not a good idea to do formal proofs in the middle of an in the middle of a lecture, but at least I want to give the basic ideas how they do this magic. So listen up. What they have to do is pre-process every given structure. Oh wait, before I do that, let me give you more motivation. Why do we care about nearest common ancestor? Yeah. So there's another problem that is equivalent to the nearest common ancestor problem, but it's amazing that it's equivalent. It's called the range minimum query problem. The range minimum query problem is and I can give you an example of the range minimum query problem. We have an array of numbers, and I'll use pi as an example. 3, 1, 4, 1, 5, 9. Let's see, where did I work it out here? Yeah, 3, 1, 4, 1, 5, 9, 2, 6, 5, 3, 5, 8, 9. I think. Anyway, so we have an array of data, and these are in locations 1, 2, 3, up to n. Okay, and the range minimum query problem says, give me I and j, tell me the place where the smallest item is between positions I and j inclusive. So if I is 5 and j is 9, then the smallest, the range minimum query would say 6, because in position 6 is where the smallest guy is between these positions. So the range minimum, so k of ij is such that a sub kij equals the min of a of I through a of j. That's the range minimum query problem. And in case of ties, we take the leftmost position where it is. Now, so the range minimum query problem turns out to be equivalent to the nearest common ancestor problem, and there's a beautiful construction that will demonstrate this, and I show you how it works. You take these numbers and you insert them into a. You aren't all going to understand this, but I got to show it to you for those of you who do understand. Let me sort them first by with the bottom component first, and so that'd be 1 2 1 4 2 6 3 1 3 9 and so on. But then I enter them into a binary tree according to the binary search tree method, ordering with the top guy first. So I'll illustrate it. So for the smallest pair here, if I give precedence to the bottom guy, is 1 2. The next smallest is 1 4. I'm going to put it into a binary tree, but I use the upper guy now as the tiebreaker. So in this case, 4 is greater than 2. Next comes 2 6. And so 6 is bigger than 4, so 2 6 is going to go here. Then comes 3 1. So I'm crossing them out. The smallest guy left based on the bottom element. So 3 1 is next. But when I put 3 1 in here, I'm going to put the 1 here to the left, because when I'm putting into the tree, I'm using the upper guy to do the sorting. So 3 9. 9 is here. 4, 3 comes in here. So 4 is tied with this 4, but 3 is bigger, so I'm going to go this way. I'm going to put the 4, 3 here. And 5, 5 will come in here. 5, 8 will come in here. Open in 5, get 5, 10 will come in here. 6, 7. So the 7 is coming in this way. 8, 3, 1, 4, 1, 5. I forgot the 9. Oh well, it's still random. So 8, 11 is going to wind up here, and 12, 9. Okay, so anyway, I get a binary tree here, a binary search tree. Well, it turns out that if you want to find the range minimum query of 2 guys, it's just the least common ancestor in this tree, the nearest common ancestor in this tree. For example, like between 5 and 9, we had 5, 2, 6, 2, 5, 3. Well, there's this 5, 2, 6, 9, 3. It's these guys here, and their nearest common ancestor is the one that happens to be highest in this tree. So this converts the range minimum query problem into a forest, a binary tree, in fact. And if I can solve the nearest common ancestor problem in the binary tree, then I've got the range minimum query problems nailed. And this beautiful construction was due to Hal Gabow and John Bentley and Bob Tarjan, I believe. And conversely, if I have a good algorithm to solve the range minimum query problem, I also have a good algorithm to solve the nearest common ancestor problem. But I don't know any algorithm for the range minimum query problem that competes with Sheber-Vishkin. So Sheber-Vishkin is the winner, as far as I'm concerned, for both of these guys. When the database is fixed, when the database is fixed. Okay. Now now I hope I motivated this enough to why somebody would care about Sheber-Vishkin's algorithm, and we now have to explain how they do it. And what they do is they map this given forest into a sideways heap in a very clever way. So first of all, we give a number to every node using pre-order of the forest. Now, pre-order is like the order of succession to the throne. So you imagine that these are kings and queens, lords, or something like this, and the first the children of Queen Elizabeth or something. And so number 1, this guy would be first. But if he dies, this guy is second. I think it's still guys in England. I'm not sure, but maybe not. But anyway, this person. And anybody knows the Alec Guinness movie where he kills off the top 13 people and then gets thrown into prison. Okay, so this is pre-order. The order succession to the throne will get 4, 5, 6, 7, 8, 9, 10. So in this ordering, the children of a family, all the descendants are consecutive. All the descendants of 1 are the nodes between 1 and 8. 2, 3, 4, and all the descendants of 4 are 5, 6, and 7, and so on. It's a nice ordering. So everything has an order now, and what we do is so I have my nodes A, B, C, D, E, F, G, H, I, J, and I associate. So I call this node V, and then pi of V will be the order of the pre-order index of V. So A is 1, C is 2, F is 3, D is 4, G is 5, J is 6, H is 7, B is 8, E is 9, 10. So this is pi of V. And the next thing, I have something called beta of V, which is really the tricky part. And I say it's the beta of V is the nearest common ancestor of all of the following set: pi of u, where u is a child or a descendant of V, not ancestor but descendant. So, for example, to figure out beta of D, this is going to be the nearest common ancestor of all of the descendants of D. Can you see him here? This is then pi of D, pi of G, pi of J, and pi of H. Right? So that's 4, 5, 6, and 7. It's always going to be a consecutive thing here, because all of the descendants are consecutive in pre-order. Okay, so what's the nearest common ancestor of those 4 nodes in the sideways heap? In the sideways heap. So if the sideways heap, there's only one sideways heap. It's this. But I'm glad you asked, because you are not the only person wondering about that. In fact, I'm now wondering which sideways heap, because I lost my picture of it. But here it is. This is the sideways heap. And so the nearest common ancestor of 4, 5, 6, and 7 is 4. Right? The nearest, okay? So if we ask ourselves then, if we have some node and its pre-order number is, let me take a random number like 20. Suppose pi of V is 20. So I have some, the 20th node in my given, the 20th node in my given forest, and now how can I figure out beta V? Well, this is going to be the nearest common ancestor of 20, 21, up to something, the last descendant of depending on how many kids or how many descendants node 20 has. And so if it doesn't have any descendants at all, so the nearest common ancestor of 20 all by itself is just 20. If I have 20 and 21, well, I didn't put that on the chart here, but you have to imagine that's 20 and 21. That's still going to be 20. If it's 20, 21, 22, even 23, it's going to be 20. But if I get up to 24, the nearest common ancestor is going to be 24, because it's a multiple of 8. So this is going to be, I'll find the one that has the largest row in here, the largest value of the ruler function. And that's what we figured out before when we had this magical relation between the ruler function in an interval and the lambda function. So in other words, the NCA of, if you remember, of J through K is actually going to be equal to lambda of K and minus J, according to the formula, or I'm sorry, 2 to this power. No, I'm sorry. No, that's not it. That's not it. It's going to be the ancestor of J at this level. So there's a formula I have to write down, but it depends on this quantity, which I can calculate just in a few machine instructions. So anyway, the gist of this is since we're running out of time, it's going to turn out that beta of beta of v is always going to be equal to beta of v. It's always going to be a fixed point, and so on. So I can work it out what beta of v is in this chart, and it's not hard. A has descendants 1, 2, 3, 4, 5, 6, 7, and so the largest guy is going to be 4 there. For B, it's 8, 9, and 10. It's going to be 8. For C, it's 2 and 3, which is 2. For D, it's 4, 5, 6, and 7 is 4. E is 9 and 10. It's going to be 10. I just choose among all the descendants the one that's divisible by the most 2's. 3. All the leaves are going to go into themselves because they have no descendants except themselves. G has 5 and 6 is going to be 6, and I is going to be 10. So anyway, that's what beta of V is. And okay, then there's an alpha of V, which is given by a formula. Alpha of V equals the sum of 2 to the row of beta of V of W for all V that go through that are ancestors of W. So anyway, there are these magical numbers that we can calculate, and it turns out that this is going to be then. Turns out this 4. This is 2 plus 4. Those of you watching it on television will be able to check me on this, but this is 4. This is going to be 8 plus 2. F is it's 1 plus 2 plus 4. You look at all the ancestors and you add together 2 to those powers of 2, and you get a binary number. Anyway, these are all numbers. This is going to be a number between 1 and n, and beta v is going to be between 1 and n, and alpha v is always going to be less than 2n. So these are numbers that we can calculate, and I will just write down the Sheber-Vishkin algorithm so that you can see how fast it is, and so we start out and we calculate. So anyway, here's the Sheber-Vishkin algorithm, SV algorithm for the nearest common ancestor of x and y. The first step is calculate h is equal to lambda of beta y ampersand minus beta y ampersand minus beta x if beta x is less than or equal beta y, or the other way around, beta x and minus beta y if beta y is greater than or equal to either one gives the same answer if they're equal. Now the next step is we calculate k, and that is alpha x ANDed with alpha y ANDed with minus 1 left shifted h. And then we recalculate h, and we change it to lambda of k ampersand minus k. 3, I set j to beta x right shift h or 1 and left shift h. And next step, I calculate x hat is equal to beta x if j equals I'm sorry, x hat is equal to x if beta x equals j. Otherwise, it's equal to tau. I didn't tell you what tau is. Of beta x minus 1. Yeah, there's another table that's called tau, where L equals lambda of alpha x ampersand 1. You get it? So, okay, here we are. All right, so, and then y bar is the same thing with x and y. What? Okay, so now tau is this little table here. Okay, I'll explain tau in a minute. First, I want to show you why the algorithm is fast. And finally, the last step is if then z, this is the nearest common ancestor, this is our answer, and it's equal to x bar if pi x bar is less than or equal pi y hat, and y hat if pi x hat is greater than or equal pi y hat. Okay, well this is the whole algorithm, and you see why I mean that it's okay. It's a finite number of steps. It goes zip zip zip, but if we count how many operations there are, this is 1, 2. Let's see. This is 1, 2. Lambda costs something, so that's 3 steps here. There's a test here. There's a test here, and there's a test here. So I have to make 3 tests, but then calculations outside of the test go this way. I can do these things in parallel. Modern computer. Here I've got 1, 2, 3, 4. Let's call this 4 operations. So I imagine that I've fetched beta x and alpha x already into a register. Or call those 2 other operations if you want. Here's 1, 2, and lambda is 3 operations. Here's 1, 2, 3 operations. Here, it turns out I have to make no operations or 8 operations if I have to do the second case, and there's maybe 8 operations calculating y hat, and then here it's just this test again. So in total, I'm making about 20 operations, 3 tests, and I have to fetch tau, lambda. I guess I counted lambda already as a fetching. But it goes zip 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 anyway. Much fewer operations than these other competing algorithms for the thing. Now, the intuition as to why it works is that you map the given forest into the sideways heap, and you put like in this part of the heap, J and G go into the heap. I'm showing the beta value. So whatever a node's beta value is, you put it there in the heap, and then everything that this turns out to be a useful operation also in other algorithms based on the sideways heap, because what it does is it takes an arbitrary forest and maps it into this nice binary structure in such a way that if several guys go into the same place, they correspond to a path in the original forest. So you divide your original forest up into little paths, and those little paths fit into the sideways heap. And then to find the nearest common ancestor, it turns out to be an easy, in quotes, calculation on the sideways heap. Because it can be done by arithmetic. Okay, so it's not one of those algorithms that I can prove easily, quickly, but when you look at the code, it's only it's only a dozen lines of code in your program, and the computer goes very fast through it. So this is I don't know, I hate to say this, maybe, do you mind if we have algorithms of the future like this that are based on mathematics that takes improving? As I say, the computer doesn't feel bad about it. The computer doesn't know if he's executing a stupid program or a subtle program. The computer just goes and follows orders. So that's a very brief and not too clear introduction, but I hope at least those of you who ever need to calculate nearest common ancestors will know that the Sheber-Vishkin algorithm is something to look at if you're going to do it. Hey, thanks for your patience getting through this. I'm ready to take questions.
Reprocessing time?
Yeah, it's linear. That's exactly the right question. Yeah, that's exercise 147. I mean, yeah, there's the preprocessing time for both the range minimum query and the nearest common ancestor goes in linear time. Although my definition was exponential time, there's actually a way to calculate these magic tables, the pi, the alpha, the tau, and the lambda table, which you might as well keep in there. All in order n time where the constant is small. Thanks for yeah.
If you were updating the tree, could you, in constant time, re-update your preprocessing? You have to do linear preprocessing. That's
too bad. Yeah, no. In that case, you get to log in. There are other methods. Very, very complicated, which I would hate to program that do these do these fast. But so the Sheber-Vishkin algorithm is good for the static case, not the dynamic case. But I like it both because it's fast, and because it's got this. It's based on theory that excites me. I mean, I think it just hangs together in a very elegant fashion. Even though it looks like you could simplify. The reason I spent 2 days on it because it looked like you should be able to simplify it. But then I showed that certain cases that occur rarely, where you can sort of have entangling things as you're doing this embedding. You actually need the complexities. I mean, the algorithm takes 25 steps or something. I don't know how to do it in 24. I think each of those steps arises because unusual cases require it. Yeah. Okay, so as I said before, a lot of people came in after. So I've got I got some freebies on the table here for Christmas presents for anyone who happens to get there first and is interested. And so Merry Christmas to all.